Okay, I promise you guys that we will show that theta hat is a legit estimator and a pretty good estimator for theta. So let's, in this section, show why this works. The Monte Carlo estimator for the integral theta hat, as we have shown, is an estimator for theta. And for any estimators of some unknown parameter in statistics, we are often interested in several of its properties. The first property we're interested in is called bias. This is given by the expectation of the estimator, theta hat, minus the true value of the unknown parameter, theta. When this is equal to 0, it means that the expectation of the estimator is equal to the true parameter. In that case, we call this estimator unbiased. The second property we're interested in is consistency. We also call it asymptotic consistency of the estimator. This means that intuitively, as the sample size gets larger and larger, does our theta hat get closer and closer to our true value or true parameter theta? We say that an estimator theta hat is asymptotically consistent if, as n goes to infinity, the probability that the absolute value of theta hat minus theta greater than some arbitrary epsilon value goes to 0. We'll talk more about this later. The third property we might be interested in is called efficiency, and this can be captured by the mean squared error of the estimator. By definition, that is the expectation of the square deviation between theta hat and theta. We're also interested in the asymptotic distribution of our estimator theta hat. For example, sometimes we can find that it's asymptotically normally distributed. At other times, as sample size goes to infinity, the theta hat has different other distributions. So we will talk about efficiency and asymptotic distribution of theta hat later. For now, let's show that theta hat, the Monte Carlo estimator for theta, is unbiased and also consistent. Let's first show that it is unbiased, and this is quite easy to show. In order to show that our theta hat is unbiased, we only have to show that the expectation of the theta hat is equal to the true parameter or the true value of the integral theta that we're trying to find. So what exactly is expectation of theta hat? We know that theta hat is obtained from 1 over n times the sum from 1 to n of g of xi's. So we know that the expectation of theta hat is equal to the expectation of 1 over n times the sum of the gxi's. Now, 1 over n is a constant, so we can pull it out. And then this will become expectation of the sum of the gxi's. Now remember that each of the xi's was an independent and identically distributed draw from the uniform distribution. So the expectation of the sum is equal to the sum of the expectations. And because each of them is identically distributed, we know that this should be equal to 1 over n times the expectation of g of x. And the 1 over n and the n can cancel out. We're left with expectation of g of x, which is by definition our theta. So we have shown that the expectation of theta hat is equal to theta. In other words, our theta hat is unbiased. Now, in order to show that theta hat is a consistent estimator of theta, we will need to show that theta hat converges in probability to theta as our sample size n approaches infinity. In other words, for any epsilon, arbitrary epsilon greater than 0, we want to show that the limit as n approaches infinity of the probability that the absolute value of theta hat minus theta exceeds epsilon goes to 0. Intuitively, it means the following. For any arbitrarily small positive number epsilon, say 0.01 or 0.001, the chance that the distance between theta hat and theta exceeds this arbitrarily small number epsilon goes to 0 as n approaches infinity. In other words, as our sample size gets large, the chance that the distance is greater than this arbitrarily small value gets smaller and smaller, and eventually it approaches 0. In order to show that the theta hat converges in probability to theta, we will need to use the Markov's inequality, which you probably have learned in 410. But we'll just briefly review it over here. So the Markov inequality is given in the following theorem. Let x be a non-negative random variable and let a greater than 0 be some non-negative or positive constant. Then the Markov inequality states that the probability that x is greater than or equal to a is always less than or equal to the expectation of x divided by a. Okay, so now let's move on back to showing theta hat is a consistent estimator of theta. In other words, it converges in probability to theta. We want to show that for any epsilon value greater than 0, the limit of this probability goes to 0. It's going to be equal to 0. So let's first find out what exactly is this probability. So probability of the absolute value of theta hat minus theta exceeds epsilon if we take the square of both sides is equal to the probability that x hat minus x squared is greater than epsilon squared for some arbitrarily chosen positive constant epsilon. Now, let's notice that this part in blue, x hat minus x squared, is going to be a non-negative random variable. So we can apply the Markov's inequality to this thing. And by the Markov's inequality, we know that this is less than or equal to the expectation of the blue part divided by epsilon squared. And the expectation of theta hat minus theta squared is actually just the variance of theta hat. This is because the variance of something is equal to the expectation of it minus its mean. And earlier we showed that theta hat is unbiased, meaning that its mean is equal to theta. So this is just the variance of theta hat. So now on the numerator, we have the variance of theta hat, and on the denominator, we have some arbitrarily chosen constant, epsilon squared. Now, let's notice that the variance of theta hat is equal to the variance of gx bar. So this is given by the variance of 1 over n times the sum from 1 to n of the gxi's. And we know that the variance of a constant times something is equal to that constant squared times the variance of something. So we can first pull the constant 1 over n out and square that. And then inside we again have the variance of the sum of the gxi's. In this case, because each of the xi's are independent and identically distributed, the variance of the sum is just going to be n times the variance of g of x. And that gives us that the variance of theta hat is equal to 1 over n times the variance of g of x. Now, earlier we mentioned that the function g of x is integrable or bounded on the interval from 0 to 1. So let's use u and L to denote its upper and lower bounds. So I flipped the lower and upper here, but you get the idea. So let's use u to denote the minimum of the maximum of g of x in the interval from 0 to 1. And let us use L to denote the lower bound, which is the minimum value of g of x in this interval. Then it is quite obvious that the variance of g of x, which is given by the expectation of g of x minus the e of g of x, so theta squared, is going to be less than or equal to u minus L squared. Therefore, we know that the probability that the absolute distance between theta hat and theta exceeds an arbitrary epsilon is less than or equal to variance of theta hat divided by epsilon squared, which is less than or equal to 1 over n of u minus L squared divided by epsilon squared. Okay, so now we can see that here, epsilon is a pre-chosen constant. So are u and L. These are pre-chosen constants. And as n goes to infinity, 1 over n goes to 0, and we can see that the right-hand side over here will also approach 0. And thus we have shown that as n goes to infinity, this probability goes to 0. In other words, our theta hat converges in probability to theta. So we've actually shown this step by step, but this is actually probably something you have heard of before, which is the weak law of large numbers. In other words, our sample mean converges in probability to the theoretical mean. To summarize, if we want to evaluate theta, which is equal to the integral from 0 to 1 of g of x dx, we can first draw n random samples. Xi each follows uniform 0, 1. And then we can estimate theta by theta hat, which is given by the arithmetic mean of these g of xi's. The theta hat that's estimated this way is an unbiased estimator of theta, meaning that the expectation of theta hat is equal to theta, and it is also asymptotically consistent, meaning that as our sample size n goes to infinity, theta hat will converge in probability to theta.